Hi, I'm Aaron Sampson, and in this course I'll cover architectural concepts including wired and wireless topologies, network types, technologies facilitating the Internet of Things or IoT, and wireless technologies. In this presentation, we'll take a look at various types of network topology. Now, topology itself refers to how things are designed, how they're laid out, and how things, in essence, take place within a specific design framework. But every network has both a logical topology and a physical, and we'll talk about the logical first. This refers to how data is transmitted between nodes, the way that signals respond on the network media. Now, this is a function of the network protocols in use to transmit the data across a network. For instance, Ethernet. That is a protocol, in a bit of a looser sense, if you will, when compared to something like TCP/IP. Ethernet, however, is still a set of rules, a set of guidelines as to how things take place. For instance, it's the ability to share a single media at the same time and handling collisions if and or when they occur. That is, in essence, the basis of Ethernet. So that is not necessarily a function of the network's physical topology, the way that it is actually laid out. You can implement an Ethernet topology on various different types of physical topologies. So that's the difference. The physical does not really care about the logical. The logical does not really care about the physical. But the physical topology does represent the actual layout of the network devices, how they are arranged, how they are interconnected, and how they communicate with each other. So we are actually talking about hardware and cables and things along those lines when we talk about physical topology. So looking at some of those physical topologies, there are several different types, and these days this or something like it is certainly the most common, the star topology. Each node is connected directly to a central hub or switch, and that can include file servers, workstations, or peripherals. And of course there can be other switches as well. These days we are probably fairly familiar with the big rack of switches that are all interconnected to each other, but then every system is connected to that rack of switches. So it quite simply means that there is a central connection point for all systems. Whether they actually look like they are arranged in a star doesn't really matter. It's the central connection point that refers to the star. In terms of advantages, it's easy to implement, it's easy to troubleshoot or upgrade. There are some disadvantages. If the central hub or switch fails, then everything attached to it will be effectively disabled. So in this very simple example, if that switch went down, clearly nobody could communicate with anyone. So in a lot of cases, you might see some redundancies implemented to address that. And again, that's much more common these days because the cost of hardware has gone down so much, but in earlier days, it wasn't as easy. A ring topology is rarely used in today's LAN environments, but you might still find it in some ISPs for high speed and resiliency. The idea behind a ring is that each node in the ring is responsible for passing information to and from each other. So you can only communicate with systems that are directly next to you in a ring. So you have to pass the data from yourself to the next system, which then passes it to the next system, and so on and so on and so on. So they aren't particularly fast. If, for example, that file server had to submit a print job to the network printer, it would have to go through the two computers in between to submit that job. So again, it's not particularly fast, and that's why you don't see rings very much anymore. It did, however, have an advantage of reducing the chance of collision, and in fact, if it's what's known as a token ring, collisions don't happen at all There is just a token, which can be thought of as a little container that circulates around the ring. And as any system needs to communicate, it places data into the token and passes it to the next system. When it reaches at the destination system, that system pulls the information out of the token and it just keeps circling it around. So in token passing on a ring, collisions don't happen at all, but it's fairly slow by comparison. Another disadvantage is that if one node goes down in this type of ring, it will affect the entire network. If that file server went down, then it breaks the ring. So communications fail for everyone. Now, a mesh topology is where you see one system connected to every other system. So there are many redundant connections. Now, the devices will process their own data in this regard, meaning that there just is no central connection device. There's no hub or switch or anything that handles address tables or anything like that. So it's fairly complex to implement a mesh. And it does offer some advantages with respect to being able to withstand high traffic volumes. It's quite resilient because of the redundant paths, and you can expand it without interruption. You can add more links because there are several other links already there, but because of that complexity, it is difficult to manage and it can be quite expensive. Typically what you might see are some of the more critical systems set up as a mesh, so that there is some redundancy, but then they would also be connected to a standard star. So the star would be kind of the normal method of communication, and the mesh would be there as a fallback or as a means to handle additional traffic or perhaps dedicated types of traffic. So you do still see a certain amount of mesh topologies in networks these days. Now, the bus topology is what's also known as a linear bus, and you can see basically this main backbone or trunk running down the center, and then you have these peripheral systems, and I don't mean peripheral in the sense of a printer, they just branch out from the sides. So each system is directly connected to that main trunk. You have to have two defined termination endpoints for this, so that signals quite literally do not reflect back when they hit the end of the wire. So a terminator, in essence, has resistance so high that it just kills the signal. But in a bus, all devices receive all messages, so it's not particularly effective, and this is quite a legacy design. I can't imagine you would see a bus topology anymore in today's environments. It did have some advantages. It was easy to set up. It required fewer resources, again, no central connection device, and it was relatively inexpensive, but had some disadvantages. It was limiting in terms of how large it could get. It was difficult to troubleshoot. If a system went down, it was hard to know where the problem was occurring. And it was somewhat vulnerable. Again, back in the early days, it was not uncommon to see wire tapping happening. You could quite literally tap into the wire physically to pick up on the signals and effectively listen to what was going on those networks. So again, there are these several types of topologies, but certainly in today's environments, the most common you would find would be some implementation of a star, the central connection device to which all other devices are connected, but those again represent the physical topology. Then the logical refers to how communications occur within that physical framework. In this presentation, we'll take a look at the two basic types of wireless networks, beginning with what's known as the ad hoc. Now, this is still a local area network that is built as devices are added and connected to each other. Each device can connect to the wireless device itself and to each other. But it's referred to as ad hoc because there really isn't any defined infrastructure in place. All you need is the wireless device itself, in this case, a broadband modem, and a connection to the internet with an internet service provider. From that point, things can happen quite on the fly, if you will. You can connect systems with an Ethernet cable, and of course, you can also access the wireless. So this offers the advantages of bypassing the need for a router. Now, let me clarify that statement. It more so means you do not have to go out and purchase a dedicated router. In this case, the broadband modem itself is the router. It handles the connection to the internet and also handles the switching aspect of systems being able to see each other. And again, that can be over a cable or over the wireless. So most of the home routers, for example, do have 4 ports to which you can connect any type of device, and they, of course, can then just see each other in a very LAN type of fashion. But once you run out of those physical wired ports, then every other device can simply connect wirelessly, and that creates a LAN. So you have a router and a switch all in one. So again, as mentioned, you just do not need a dedicated router is what that is referring to. So the devices connect to the other devices on the network to access and share files. And of course, this is much more affordable than a traditional network. We really don't need any hardware other than the broadband modem itself, and again, a connection to the internet. So if desired, every other device can connect wirelessly, and you don't need any additional hardware. So it's very fast, very simple, very easy to set up. Now, it's also very mobile. The network can be created on the fly, and it only requires 2 or more devices, the modem itself, and then 1 more device. And again, very easy to set up. You can quickly connect multiple computers with no additional hardware. And really all that's needed in terms of a connection is the device itself being able to take advantage of wireless communications, which these days can be just about anything. Computers, laptops, phones, PDAs, printers. So again, just very simple, very flexible, and very inexpensive. So a lot of advantages, and of course, you almost always see this in the home environments, as well as small offices, things along those lines. Very easy to set up a network with minimal infrastructure. So kind of the opposite of that, if you will, is the infrastructure mode. In this case, we do have a physical network, if you will, in terms of switches, routers, cabling, things along those lines. So that represents the infrastructure that is already in place. So then what you do is you simply add a wireless access point, or an AP. That extends the capability of this physical infrastructure to the wireless devices, but it's all the same network. So the WLAN, the wireless LAN, does not replace the wired. Instead, it just extends its functionality. So again, in the graphic, we see those 3 laptops connecting through the access point are then able to see all of the other resources that are on the wired network. So again, it just extends it. So in terms of the advantages, this is very scalable. Using multiple access points, you can reduce congestion and increase the overall coverage area, and you can roam between interlocking access points without losing a connection to the network. So in larger corporate environments that are simply too large for something like a home router to cover, you just have multiple access points, and as you leave the boundary of one, you enter the range of another one, and you just don't ever lose your connection. A common example of this, something like an airport. I'm sure most of you are familiar with the fact that you can connect to the wireless at an airport and remain connected as long as you are in that airport. And the reason I'm using that as an example is because they are, of course, very large, and you just don't lose coverage in most cases. No matter where you go, you maintain that connection, and that is because of the multiple access points. Another common example, hotels. From floor to floor, you still remain connected to the network. So again, this is why it's referred to as infrastructure mode, because you still have that physical infrastructure in place. Now, there are some drawbacks. It's a little more complex to set up compared to an ad hoc, and it can certainly be more expensive to set up as it requires the access point and or access points. And of course, there is still the physical infrastructure, but that typically represents something that has already been implemented. So it's not so much an extra cost, but you still did have to make the initial investment. So the access points themselves aren't particularly expensive, but they certainly give you the advantage of being able to extend that physical wired infrastructure to the wireless clients.
In this presentation, we'll take a look at the various classifications of network types, more or less with respect to their size. So the first one is the LAN, the local area network, perhaps the most familiar. This is a smaller computer network that is typically confined to a single room, a single building, or possibly even a group of buildings, but ultimately they just aren't that large. So an example is, of course, an Ethernet LAN. This is perhaps one of the most common implementations when you walk into any office. For example, they will most likely be using an Ethernet LAN. Now, in terms of characteristics, the topology is certainly taken into consideration. This is the arrangement of the devices. And again, the star topology is the most common. It takes into consideration the protocols, the rules, and encoding specifications, and the media, the cables that you're using. Those are all just characteristics of a LAN. So again, a star topology of an Ethernet protocol is, of course, one of the most familiar LAN configurations. The next type is the wireless LAN, or WLAN. This is really just enabling communications in a LAN environment, but over wireless protocols. So instead of having to physically connect them with a cable, we just allow access using radio frequencies. So the access point represents where our devices can connect, but of course, they do not need cables. And of course, this is very common these days at home or smaller offices, and certainly larger environments as well, depending on the nature of that environment. One key aspect is security, but certainly wireless is very convenient, very easy to connect because of the lack of any kind of physical cable. So common devices include mobile phones, laptops, tablets. And as mentioned, you commonly see this implemented for home use, small businesses, or any business, of course, but more common in smaller environments. And of course, the public internet. So when you go to a coffee shop, for example, you connect to the wireless or to a hotel or an airport, things along those lines. Some networks, wireless or otherwise, are not really about creating a broad network, but just point-to-point connecting a peripherals or other devices for the purpose of uploading, downloading, or synchronization. That's what we call a personal area network, or PAN. Currently, these tasks are often done wirelessly with the use of Bluetooth. Now, the next is the Metropolitan Area Network, or the MAN. This is a data network design typically used for a city or a town. So it's similar to a LAN, but it is more so a collection of LANs, where you might see things like a central office or a headquarters and several branch offices that are relatively in the same geographic space, generally something about the size of a city. So you connect the LANs together. Now, this is effectively the same approach as a WAN, a wide area network, which we'll talk about in a moment, but it's just a smaller scale. So again, you might see this in large organizations that do have multiple locations, but again, still relegated to the same metropolitan area. Now, this does have several benefits: efficiency, fast communication, high-speed carriers such as fiber optic cabling. They typically have dedicated communications, so you aren't sharing those connections with anyone else like you might be if you were using the public internet and VPNs, for example. So this allows for a number of benefits. Now, the WAN is the wide area network, and this is any kind of computer network that spans a large geographic area. And perhaps the most commonly known WAN is the internet. So it has to consist of at least 2 local area networks, but as mentioned, the internet is by far the most common example of a WAN. Now, if you were to scale this back to, let's say, one corporation, then you could replace the internet perhaps with a telecommunications provider, and you can still use dedicated connections as opposed to the public internet. But again, really the only difference is the scale. WANs can be across an entire country, an entire continent, even global. So it's a combination of the same technologies that are often used for metropolitan area networks, just a larger scale. Where a MAN might be confined to a city, a WAN really is not confined at all. Now, a CAN is a campus area network, and this is kind of a middle ground. This typically involves proprietary local area networks that generally serve corporations, universities, or government agencies. So again, kind of a middle ground between the LAN and maybe the MAN, because it might not expand to an entire city, for example. As its name indicates, a good example is a college or university campus. They can be fairly large, but certainly not an entire city, if you will. So the same technologies are used to connect administrative buildings to residence halls, to libraries, to the athletic facilities, and to the student centers. So we see geographically separated locations that are still interconnected, but again, not quite to the degree of a metropolitan area network. And finally, the storage area network, or SAN, is a specialized, high-speed network dedicated to granting block-level network access to storage. So what this means is that the servers, typically down at the bottom of the graphic, do not really use their own internal storage if they even have it. They instead use the network to communicate with a huge rack of nothing but hard drives. And they only access a dedicated portion of that array. So one server would not access the entire amount of storage. It's block by block by block. But as far as the end user is concerned, the server, that storage appears to be local. But you can get tremendously high amounts of storage in terms of capacity in a SAN, as well as very high levels of performance because it is dedicated. So the common uses include applications that need to be highly available. The data can be stored on the SAN, and it's much more resilient because there are typically a lot of redundancy features built in. And the applications can perform very well because you offload the storage functions to just the SAN. So each server just does not need to manage its own storage anymore. It offers storage utilization, you can consolidate resources, and you can create tiered storage levels. So if any one application needs very fast access to storage, you can ensure that it's accessing the fastest drives, such as solid-state drives compared to magnetic traditional drives. And you can also implement better data protection and security because everything is centralized in the SAN, where there is typically dedicated backup procedures, dedicated redundancy features, and dedicated security personnel to ensure that the data remains safe. So again, there are multiple different types, and you'll hear these terms quite a lot as we move through the course and as you get into a networking environment. Certainly the LAN would be the most common, but many other environments do implement MANs, SANs, PANs, and even WANs when appropriate to facilitate those different geographic areas and dedicated types of storage access.
All right, in this presentation, we'll take a look at what's known as IoT, or Internet of Things. And this refers to the continuous growth of Internet-enabled devices, as well as the communication that occurs between them. And this is certainly something that is becoming much more common. We are, of course, all familiar with standard Internet connectivity using traditional devices such as desktops, laptops, and smartphones. But many other types of devices are becoming capable of doing so as well. Watches, appliances, lighting and power in your home, entertainment systems. Of course, we know we can pair our smartphones with our cars and things like that. So there is just this much broader scope of interconnectivity between devices. Now, with respect to that interconnectivity, some of the protocols that we'll see here aren't necessarily appropriate for true internet connectivity, but more so just for communicating with each other. But it should be said that the amount of devices that will ultimately be able to communicate over the internet is certainly increasing, and that in part was one of the reasons why the TCP/IP version 6 protocol has such a dramatically increased address space in terms of the number of addresses available. Again, it is just trillions upon trillions upon trillions. So this will absolutely accommodate the total number of devices that might need to be able to access the internet. But some of these protocols that we will take a look at here are more so just for device-to-device communication. And the first example is known as Z-Wave. This is a wireless communications protocol typically used for the automation of home devices. So your heating, ventilation, and air conditioning, home cinema or entertainment systems, your security system, a garage door opener, a propane fireplace or an electric fireplace, and along those lines. Anything that really can be controlled with an electronic chip can communicate with any other device with an electronic chip using a protocol such as Z-Wave. So again, many of the home automation systems implement this protocol. ANT is an open access wireless services network technology that typically employs a sensor network type and operates at 2.4 gigahertz using ultra low power. So where you tend to see these are in fitness monitors, heart rate monitors, bike speed, temperature, things along those lines. So you see these multiple sensors that communicate with some kind of master device or a hub. And the hub is simply responsible for controlling the communications, and that can even communicate with another hub. It's not so much a hub like we think of in Ethernet. It is simply just a master of communications, if you will. So it is the control center. Bluetooth, and what's also known as Bluetooth Smart. Now, Bluetooth in and of itself has been implemented for quite some time, and again is used in a number of devices for just communicating with other types of devices. It's a short range transmission that is used generally for computer peripherals such as mice and keyboards, things along those lines. And of course, these days, smartphones and pairing with your car and things along those lines. So Bluetooth in and of itself is certainly not new, but there is an implementation of Bluetooth known as Bluetooth Smart. And this really has been designed specifically for Internet of Things types of communications. So it's very energy efficient. It's a low power alternative to Bluetooth. It offers compatibility across a number of smart devices. And typically you'll find it implemented when things like location needs to be known. So precise locations, in essence, can sense when you leave your house, for example, and simply that act can turn off the lights, or conversely, when you arrive, it can turn on the lights, and really any other number of devices. So again, it has been designed specifically for this type of scenario so that it can pick up on where you are or where this particular device is, and based on that, pre-programmed actions can be triggered. NFC is near field communication, and this is a form of contactless communication supported by devices such as smartphones and tablets. Very fast and convenient because there's virtually zero configuration. For the most part, you just place the devices close to each other and NFC picks up on that. So as soon as they are within range of each other, then they can start communicating. So a number of different types of devices, again, can use this. And one of the earliest implementations was in laptops. If you placed two laptops with NFC communications capabilities very close to each other, or even pointed a directed communications portal, if you will, toward the other one, they would instantly sense that and you could start transferring files. Now, some of those use different protocols, but NFC can in fact use a few different actual protocols to transfer data or print jobs, for example, but NFC in general is just this near field. As soon as they are close to each other, they pick up on this fact and can then communicate. RFID is radio frequency identification. These devices use radio frequency waves to communicate over low frequency, high frequency, and ultra high frequency bands. And you'll find these typically implemented in a number of scenarios that we'll take a look at in a moment. But one of the more common ones is when you have any kind of a chip that needs to be read, such as what's on your credit card or bank card, if you use a tap payment system. There is a reader, of course, which is the pin pad itself, but all you have to do is tap it, and that triggers a response by the transponder, and of course transmits the data back and forth. But you might see other implementations, including access control. And in that regard, we aren't referring to like permissions or things along those lines, but actually getting through a physical door, for example. If you have a smart card, anything with a chip that can be picked up on, and you just tap a pad and that opens the door. Asset tracking, parking management, patient ID management, inventory management, basically anything or anyone that can be tagged can be picked up by the antenna that you see here, which is fed to a reader, which is connected to a computer, which can in turn register the transmission between the antenna and the transponder. So you can track inventory as things come and go by just scanning them, of course. And finally, certainly 802.11. Now, if you are familiar with this actual specification, you won't be surprised to learn that this is for just wireless networking. I'm sure most of you have heard of 802.11. If you're ever wondering where the name came from, it in fact was the IEEE task force that was created in 1980 in the month of February. That's where the 802 came from. And then they came up with 12 specifications for different types of communications, and 11 covered all wireless. So it has now been refined into A, B, G, N, and things along those lines, and we'll talk about those later on. But it is quite simply the process of using radio frequencies at low energy consumption to support a wider coverage range, including the Internet of Things. But we see the transmission bands that are used: 900 megahertz, 2.4 gigahertz, and 5 gigahertz, in essence, depending on the implementation and the application for this protocol. But of course, 802.11 is the familiar home internet type of communication that you find with wireless routers. So ultimately, all of these things can be used in one way or another for all of this new interconnectivity of all of these new types of devices that are able to communicate with each other and even over the internet. All right, for our exercise this time, we'll ask you to describe the different wired topologies, then to describe the different wireless topologies, then to describe the different network types, and finally to describe the Internet of Things. So what we'd like you to do is take a few minutes, pause the recording, jot down some responses, then we'll come back to review and we'll see how you made out. So we'll see you shortly. All right, so to review, our first question was about wired topologies, and here we find the star, the ring, the mesh, and the bus. And these days, almost every implementation is going to be some form of a star. You'll have a central connection point, which could be a single switch or multiple switches, but everything basically connects to that centralized point. You might still see some mesh along with that to improve redundancy in case something fails, but rings and buses are very uncommon these days. In terms of wireless topologies, we have the ad hoc and the infrastructure modes. Ad hoc requires basically nothing more than the wireless device itself, which performs both routing to the internet and switching for connected devices. And you can connect those devices with an Ethernet cable or, of course, wirelessly. So there's very little structure required. Your clients can come and go. Really, anyone who has the security, of course, can connect to the network. You can have any number of devices. It's certainly up to you to control, but beyond the physical wireless access point or the wireless router, there's really no other infrastructure required. Infrastructure mode is rather the opposite of this. We already have a network in place, a standard or traditional wired network, if you will, where we have clients and servers and printers and various other devices. Then we just extend the capability of that network by adding wireless access points. So they simply extend the connectivity to wireless clients so they can connect to the same network, access the same servers, the same printers, and of course, internet through an already existing dedicated router. So typically you'll find infrastructure mode used in offices, in hotels, in airports, things along those lines. Ad hoc would be a little more at home or small offices. Then we asked about the network types, and we have several different types here. The local area network, the wireless local area network, the campus area network, metropolitan area network, wide area network, and storage area network. Now, as you move from LAN up to WAN, really it is just the geographical size that is increasing. But storage area network is a different type altogether. It is dedicated to just accessing storage. So it's not designed for interconnecting your clients and servers, for example. But again, when it comes to LAN, WLAN, CAN, MAN, and WAN, those really are very similar in nature. It's just that they cover a much larger geographical area as you increase. And finally, the Internet of Things refers to the continuous growth of Internet-enabled devices and their interconnectivity. The capability of just about every electronic device to be able to communicate with other types of electronic devices is really where this is headed, so that eventually just about anything that has a chip in it really can have an IP address and communicate with other types of devices, so that you can implement things like home automation and various other types of interconnectivity between appliances and smart devices and things along those lines. So it is something that is definitely on the grow, if you will, and really should only increase the capabilities of electronic devices to communicate with each other. So hopefully you made out okay with those tasks, and if so, we are ready to move on. Earlier, we touched on some of the basic characteristics of wireless communications as defined by the 802.11 specification. But that was quite some time ago, and there have been a number of enhancements and refinements to that specification since. So in this presentation, we'll take a look at several of them, beginning with 802.11a. Now, this was created as an extension to the original 802.11 standard and supports a higher bandwidth, up to 54 megabits per second, and a frequency spectrum around 5 gigahertz. Now, that higher frequency does offer a better quality signal, but by nature, higher frequencies do not travel as far as lower ones do. So it shortens the range of A networks, and further, the higher frequency makes the A signals more difficult to penetrate obstructions such as walls. Now, that's not necessarily a downside, if you will. Sometimes you might actually want to restrict the network a little bit more, condense it, if you will, or confine it to a shorter range. And if it's more difficult to get through things like walls, that might actually provide a little more security. So again, depending on your perspective, it might not really be a downside. So in terms of the pros, it does offer that higher speed and the use of regulated frequencies, meaning that other devices do not use this frequency. It has effectively been reserved. So this prevents signal interference. But on the downside, it can cost more, and again, can shorten the range and be more easily obstructed. So if you are looking for a wider range that penetrates more easily, then yes, this is certainly a con. Now, B supports bandwidths of up to 11 megabits per second, so considerably slower. This is comparable to the traditional Ethernet, around 10 megabits per second, and that in and of itself is quite old these days. And it also uses unregulated 2.4 gigahertz signaling frequency, meaning a lot of vendors, a lot of devices use this same frequency. But since it is very commonly produced, this can lower the production costs. So ultimately, it can interference from devices using the same 2.4 gigahertz range. Some common examples are microwave ovens, cordless phones, and various other appliances, so they can disrupt the signals. So in terms of the pros, it is a lower cost and it has that better range and it's not as easily obstructed, but on the con side, it is the slowest maximum speed and again, susceptible to interference because of that unregulated frequency band. So you might think, well, if it's not as fast as A, and it suffers from possible interference, and simply the fact that it uses the letter B, you might think that it came out after A. In fact, A and B were released at the same time, and it really just comes down to what you prefer. If you want the lower cost and the better range, you went with B. But there was the trade-off in that it wasn't as fast. But A was faster, but more easily obstructed and things along those lines. Didn't travel as far. So there was always the trade-off in either case. So along came G, which emerged in 2002 and 2003, and this combines the best of both A and B. It supports the higher bandwidth of up to 54 megabits per second, but uses the 2.4 gigahertz frequency for greater range. This was also backward compatible. In other words, it worked with the already in place B wireless adapters that you might have had. So we don't have to change out all of our adapters to take advantage of the higher speed. In terms of the pros, you get that fast maximum speed, again up to 54 megabits per second. You get good signal range, which is not easily obstructed, but it could have been more expensive than the B that was already implemented. Plus, since you did already implement the B, you are looking at basically junking all of that and incurring the extra cost of a new infrastructure. Plus, it still might suffer from the interference because it was using 2.4 gigahertz. So then N came along. This was often referred to as just wireless N, but this improves on G by offering greater bandwidth and utilizing multiple wireless signals and antennas instead of just one. This is known as MIMO technology, which we will actually talk about later on. Very quick and short, it is multiple antennas as opposed to just one. A lot of the early wireless routers had a single antenna. So this can support bandwidths of up to 300 megabits per second and a better range and increased signal intensity. So in terms of the pros, we now have the fastest maximum speed, 300 megabits per second, the best signal range, and the most resistant to signal interference, and it's still backward compatible. Cons, the standard is not yet finalized, so it may affect things moving forward, and again, it's more expensive than 802.11g. Then we have 802.11ac, which is the newest generation of Wi-Fi signaling. This utilizes dual-band wireless technology, which means it supports simultaneous connections over both 2.4 and 5 gigahertz. It is backward compatible with 802.11b, g, and n, and supports bandwidths that have been rated up to 1300 megabits per second on 5 gigahertz and 450 megabits per second on 2.4. So significantly higher, in fact, in both cases, using either frequency. So again, this really pulls together the best of everything, but this can certainly be a little more expensive as well and does represent yet another upgrade. So if you have already implemented your existing infrastructure with something else, once again, you are looking at another upgrade. So there certainly can be those downsides as well. Ultimately, you just want to try to ensure that you have good range, good signal quality, good speed, and of course security, but at the same time while not having to continually upgrade and incur additional costs. In this presentation, we'll take an introductory look at some of the types of mobile or cellular communications, beginning with what's known as GSM, or the Global System for Mobile Communication. This is a digital mobile telephony system that currently represents over 82% of all global mobile connections. Now, it operates at one of two frequencies, 900 or 1800 megahertz, and of course, fundamentally just digitizes and compresses data prior to sending it down a channel. But one of the inherent challenges is, of course, the tremendous number of people using mobile communications these days. There are billions worldwide. Now, of course, not all of us are communicating at the same time using the same towers, but there are still quite a few at any given time. So we need a way to better accommodate multiple users. And one approach is what's known as TDMA, time division multiple access. Again, multiple people using the same media at the same time. So this is a technology used in digital cellular communication whereby the channels are divided into 3 time slots. This increases the amount of data that can be carried, essentially threefold. Now, this is used by digital advanced mobile phone services, or DAMPS, GSM that we just talked about, and personal digital cellular. Those are just different types, and DAMPS and PDC, in essence, make up the remaining percentage of communications. But the idea behind TDMA is that each channel, and there are a tremendous number of channels available, is divided by time, and then each user or each device synchronizes to that time. So when I'm communicating, I use time slot A. When you are communicating, you use time slot B, and someone else uses C, and we only pay attention, if you will, to the data in our specific time slots. So I don't hear your conversation, you don't hear mine, because of the difference in the time slots. Now, this does require some pretty specific synchronization, but voice data is not all that much. So in other words, it's not a big deal to break it up into these smaller chunks, if you will. And it accommodates multiple users on the same channel. So again, we can increase the overall throughput 3 times per channel. Now, another method of accommodating that multiple access is CDMA, or code division multiple access. This is used in second generation 2G and third generation 3G wireless communications. And I'm certain if you have a mobile device, you are very familiar with what we call 3G. So this is just another form of multiplexing, which allows numerous signals on a single transmission channel, and this optimizes the available bandwidth. It's commonly used in ultra-high frequency cellular systems running at either 800 megahertz and 1.9 gigahertz. But the idea is that each transmission has a specific code attached to it, and your device is programmed, for lack of a better word, to only pay attention to the specific code that matches your connection. So again, my conversation uses code 1. Your conversation uses code 2. We only pay attention to the appropriate code. So again, I do not hear your conversation. You do not hear mine. So this way, again, we can facilitate multiple access over the same channel. So in terms of the benefits, this offers good quality signal. There's no division in terms of the time. So the signal quality is a little better. It offers flexible allocation of resources. It's easily scalable because you can just add more codes, and it's compatible with other cellular technologies. Disadvantages: as the network grows, overall quality of service decreases. If you end up with too many codes, that's a lot of processing. So the more devices, the more codes you need to maintain and manage. So in essence, it can become a bottleneck. But ultimately, that is how these days we facilitate the multiple access requirements of cellular communications. In this presentation, we'll talk about frequency with respect to wireless communications and ultimately how it affects the overall amount of data that can be transmitted, as well as some other characteristics. But the term itself quite simply represents the number of complete cycles in a single second. And I'm sure that's nothing particularly new. We've been using this term in various components of computing for a very long time. For example, our processors. We always describe them as being 3 gigahertz processors, for example. That means they can process 3 billion times per second. And in terms of wireless communications, the 2.4 gigahertz frequency means it cycles 2.4 billion times per second. So again, it is quite simply how often something occurs. Now, in terms of radio transmissions, lower frequencies correspond to a longer radio wavelength. The length is the distance between the two peaks or the two troughs, for example. So if you imagine that graphic as a bit of a spring and you grab hold of the end and stretch it out, you are increasing the distance between the peaks or the troughs. That is a lower frequency. It's happening less often within the same space, so the space between them gets longer. Conversely, higher frequencies correspond to a shorter radio wavelength, So again, if you imagine that as a spring, then you would squash it in and you would decrease the distance between the peaks or the troughs. So again, a shorter wavelength. Ultimately, it is quite simply how many of those peaks or troughs occur in 1 second that dictates the frequency. Now, when it comes to wireless communications, this was defined by the IEEE 802.11 specification, and it operates in several unlicensed frequency ranges. Now, this is actually quite important. You see 2.4 gigahertz there, and that has for a very long time been a standard, but it's actually not always exactly 2.4 gigahertz. There is a range between 2.4 and 2.5 that is actually used, and there are varying values within that range for different types of transmissions. Now, we'll talk about that in greater detail later on, but it is not always exactly 2.4. And the same thing goes for the 5. We call it 5 gigahertz, but it's actually 5.15 up to 5.875. And the unlicensed component, in essence, means that it's not reserved. There are other things that can use those same frequency bands if necessary. There are certain transmissions that are licensed. They are reserved, and nothing else is allowed to transmit on those frequencies. So looking at the 2.4 gigahertz standard, this is in essence 802.11b, G, and N. And you can see that the speed changes. For B, it only supported 11 megabits per second. For G, 54 megabits per second. And for N, up to 150 megabits per second on a 20 megahertz channel width, and then 300 for a 40 megahertz channel width. Now, we'll talk about that in greater detail later on as well, the channel width, but you can see just by the math here that when you double the size of the channel, you double the overall throughput. So this is why you see varying megabits per second values from B to G to N. It's not just the frequency itself, but the channel over which it is carried and how wide that channel is. Imagine a channel like a highway. If it's a 2-lane highway, it can handle X amount of traffic. But if it's a 4-lane highway, we can imagine it can handle twice as much traffic. Now again, we'll talk about the channels in greater detail a little bit later on. So for the time being, don't worry about it too much. But 2.4 gigahertz, again, is the standard for 802.11b, G, and N with varying speeds. Now 2.4 has the advantages of a wider signal coverage. It can travel farther. Lower frequencies simply travel farther than higher ones do by nature. and they're better at penetrating walls or other barriers or obstructions, and it supports Wi-Fi B, G, and N, so it's fairly compatible. But in terms of disadvantages, there can be possible congestion and interference. Other devices, such as microwaves, Bluetooth devices, cordless phones, all might be using that same frequency range. So they can quite literally interfere with each other. So then the 5 gigahertz standard is used in 802.11a, N, and AC. And again, we see varying speeds depending on each specification. A up to 54 megabits per second, N up to 150 on a 20 megahertz channel. And then we see, again, the same doubling factor here, 300 megabits per second, if it's on a 40 megahertz channel. Then AC, in theory, can reach speeds of up to 6.8 gigabits per second with 8 antennas, all running at 160 megahertz channel widths. So again, that's not particularly common in any kind of practical implementation yet, but it does actually have that capability. So advantages of the 5 gigahertz band: it is less congested and there's less interference. It's not as susceptible because there aren't as many devices using that same frequency. It supports 23 non-overlapping channels. So again, those lanes don't overlap with each other. They don't interfere. And it supports higher network speeds, particularly when using the 802.11 AC, as we just saw. But disadvantages: it's a smaller signal area. The signals do not travel as far, nor do they penetrate as well. It also may not support older devices, so it's not as compatible. But moving forward, I think you will probably see more 5 gigahertz than 2.4 because of the speed advantage. And that's typically what we want to see these days. We always sort of assume that faster is better, but not in every situation. So again, the frequency itself really just comes down to how many times per second that signal goes from its peak to its trough and back again. And those two different frequency bands have different advantages and different disadvantages depending on their implementation and depending on which characteristic you feel is most desirable. In this presentation, we'll take a look at the speed and distance requirements of wireless communications as defined by the IEEE standard of 802.11. Now, to begin, this is the original 802.11, no letter after the number. And recall, this was quite some time ago. 802 refers to February of 1980. So when it was originally defined, the frequency was 2.4 gigahertz. The speed was only 1 to 2 megabits per second, and the transmission range was only 20 feet indoors. So quite limiting by today's standards. But as technology improved and as protocols were refined, we saw 802.11a come out, and this used a frequency of 5 gigahertz with a speed of up to 54 megabits per second and a transmission range of 25 to 75 feet. So that was certainly a lot better in terms of speed and distance, but the range could certainly be affected by obstructions. Now, that's true of any radio communications. The more obstructions and the larger they are, then the less you will receive that signal. But recall that 5 gigahertz frequencies were more easily affected by obstructions than were the 2.4 gigahertz frequencies. So then B, released at the same time as A, was still using the 2.4 gigahertz frequency, but only supported speeds of 11 megabits per second. But you can see the range was significantly better, up to 150 feet indoors. Now again, that can still be affected by obstruction, but while it's not as fast as A, it traveled much farther. So there were pros and cons of each one. Then we see 11G, again using the 2.4 gigahertz frequency, but now we have speeds of 54 megabits per second, so comparable to A, and we still have a very good transmission range, up to 150 feet indoors. And then finally, N supported both frequencies, 2.4 and 5, and a speed of up to 600 megabits per second, depending on the channel configuration, and a transmission range of up to 175 feet indoors, again, possibly affected by obstruction. But I would imagine that moving forward, we will continue to see enhancements and refinements, and really the speed should only get faster, and the range should only get farther. But in some cases, you need that backward compatibility. So, there's always a little bit of compromise, if you will. But these enhancements and refinements typically tend to just keep improving the overall transmission. So I think we'll see many more letters yet to come. In this presentation, we'll take a closer look at channel bandwidth, and this is something I referred to earlier when I mentioned how channels more or less equate to lanes on a highway, and the more lanes you have, the more traffic you can handle. So in terms of data rates, your speed can be directly affected by the channel bandwidth of a wireless signal. Now, we see two examples here, 802.11n using 20 or 40 megahertz channels, and 802.11ac using 20, 40, 80, and 160 megahertz channels. Now, n uses the core frequency of 2.4 gigahertz and AC, the core frequency of 5 gigahertz. But the question I get quite often is, well, what are these 2 hertz values? I thought the transmission was 2.4 gigahertz or 5 gigahertz, depending on your implementation. Why am I seeing these megahertz values on the channels? Well, that comes down to the basic fact that anything measured in hertz, recall, is simply a measure of how often something happens. So the core frequencies, 2.4 gigahertz and 5 gigahertz, are certainly correct. You send out a signal using that frequency. That refers to the waves, how often those waves happen in 1 second. But then you have to consider how often you can send that signal. So let me give you a simpler example. If you just speak a word, let's say the word hello, that word produces sound waves, and those sound waves come out at a specific frequency. It doesn't matter what it is, let's just call it frequency X. So you say the word hello, you just sent a signal, and the sound waves came out at frequency X. But you can, of course, say that word again, and again, and again, and again. So how many times you can say that word within 1 second refers to another measure in hertz. How many times can you send that information? So that's where the channel comes in. The more often you can say it, the more information you are transmitting. So that's where the channels allow for X amount of data, depending on how often they can support that core transmission. So again, the signal itself, the core data, is being sent out at, let's say, 2.4 gigahertz. So the channels then are how many times you can send that transmission across that channel. So those are the 2 separate hertz values. And clearly, the more megahertz you have per channel, the more times, if you will, you can send that signal. So you end up with higher bandwidth overall. Now, Wi-Fi networks, of course, use the frequency or the channels to transmit and receive data, as we know. And by default, the following channels are used, 6 and 11. So if you look at the configuration of some of those wireless routers, for example, very likely you would see those channels. And that might seem somewhat arbitrary, but there is a reason. And it comes down to the fact that The core frequencies themselves of 2.4 gigahertz and 5 gigahertz, recall from earlier, are not exactly those values. The 2.4 gigahertz specification actually ranges from 2.4 up to close to 2.5. It actually caps out around 2.78 or something along those lines. I can't remember exactly, but the point is there is a variance. And the same goes with the 5 gigahertz. And again, we saw those in an earlier presentation. It ranges from 5.1 up to about 5.8 something. Again, the values themselves don't entirely matter at this point. It's really just coming down to the fact that there is this variance of frequencies. So when we talk about 2.4 and 5, they aren't exactly those values. There is this variance. So if we have these devices transmitting on channel 6, it does not actually look like this, where you see everything going down one channel. Because of the variance, it actually looks like this, where you see some of it, for lack of a better word, leaking out onto either side of the core channel. So because of those variances in the frequency, using channel 6 actually utilizes 4, 5, 6, 7, and 8. So it's fine to have these devices on the same channel, but you are trying to cram more traffic down the same lane of that highway. Even though it spreads it across 5 channels, it's basically still the same 5 lanes of the highway. Now again, it just comes down to the total amount of bandwidth that you need as to whether or not this is a good idea. There's no harm in this per se, but if you find things are getting a little bit bogged down, you can simply change the channel. So if you were to change one of the devices to channel 7, for example, you might think you've accomplished your goal. One of them is on 6, one of them is on 7, everybody's happy. But because of that variance, because of the spread, moving one to channel 7, in fact, would not really accomplish the goal, because you'd be using 5 through 9 instead of 4 through 8. So you'd have a little bit that would be on its own dedicated channel, but not very much. So the farther away you move it, the less overlap there will be. And ultimately, if you are going to do this, then what you would want to do is something like this, moving it to channel 11. That's why you see 6 and 11 used by default, because since they both spread over 5 channels, going all the way to 11 ensures that we start at 9, whereas the other routers end at 8. So ultimately, again, it really comes down to if you feel this is even necessary. Again, there's no harm in using the same channel, but by the same token, there's no harm in using a different channel. But you've got a little bit of extra configuration now, because the other systems communicating with each router also have to have their channels adjusted. Not a big deal in a smaller environment. If you are only talking about a handful of systems, then it's no big deal to set some of them to channel 6 and some of them to 11. But then they also have been dedicated to those devices, and that might be a good thing. But if they're somewhat physically separated and the people are moving around and they end up connecting from router 1 to router 2, and their channel has been specifically set to use channel 6, let's say, it won't be able to connect to the other router. It's a different channel. So there are considerations, of course. If you need mobility and people to be able to connect to any of those routers without changing anything, then they should all be set to the same channel. But if you are absolutely trying to segregate this traffic, and you only want those clients to connect to that router and these clients to connect to a different router, then that's perfectly fine. You would isolate that traffic, and you would ensure that they don't interfere with each other, and they would always connect to the same router because they have the correct channel set. So there are always considerations, but that is the basic idea overall with respect to setting those channels and allocating and or determining the overall bandwidth available. Now, in this presentation, we'll take a look at what's known as channel bonding, and this is commonly used in IEEE 802.11 or wireless communications, and is the process of taking two adjacent channels using different frequencies and combining them. This, of course, increases the overall throughput between those devices. Now, we actually touched on this earlier when we looked at the various specifications of 802.11, the A, B, G, N, and AC, and we saw various throughputs, of course, but for the most part, if we saw a throughput of X on a 20 megahertz channel, then, of course, you could get a throughput of 2X on a 40 megahertz channel. So those widths of 20 megahertz per channel were established quite some time ago in wireless communications, but there's nothing that prevents us from taking two of them and putting them together and creating a 40 megahertz width. But of course, what happens here, let's just go with very easy numbers and let's imagine we only had two available to begin with, then clearly you are reducing the number of channels. If you take those two and put them together to create one, well, now you only have one channel. So you will inherently have fewer channels when you bond, but if you aren't concerned with the number of channels and are really only concerned with the throughput, then of course bonding is the way to go. Now, this was very popular in Wi-Fi implementations and remains so, as it provides additional functionality for what you can support, and of course that overall increased throughput. And this was initially released with 802.11n. Now, that said, there are some considerations with respect to the frequency. If you are using the 2.4 gigahertz frequency band, then you can only support 3 non-overlapping 20 megahertz channels. Recall that we also talked about the 2.4 gigahertz band and the 5 gigahertz band earlier, and it's not exactly 2.4 gigahertz. It ranges from about 2.41 to about 2.47, in fact. And this gives you a total width of approximately 70 megahertz. It might vary a little bit, but if you only have 70 megahertz in total and each channel is 20 megahertz wide, then you can only have a single bonded pair of 40 megahertz. The remainder of that band is only 30 megahertz wide, so you cannot create a bonded pair of 40 when there's only 30 left. So that said, it still does give you the increased throughput because you do at least now have one bonded channel. So this does offer a throughput of up to 54 megabits per second. But if you look at the 5 gigahertz frequency band, there is in fact a much wider range. The 5 gigahertz goes from about 5.1 to about 5.8, but it's not entirely contiguous. There are some areas in between that are kind of reserved, if you will, for other types of communications, but you can have up to 25 non-overlapping 20 megahertz channels within the band because the total width is somewhere in the range of about 500 megahertz of the usable space. So many more bonded pairs can be configured. In fact, up to 160. So that's taking two 20s to make a 40, then two 40s to make an 80, then two 80s to make a 160. So when you have a channel that wide, which is configurable in 802.11ac, then you start to see those very high throughput values that are up into the gigabits per second range. So significantly more throughput, of course. So channel bonding is, in most cases, far more flexible within the 5 gigahertz band as compared to the 2.4 gigahertz band. But it is still supported. You just have a little more flexibility and, of course, the greater throughput if you configure this within the 5 gigahertz band. In this presentation, we'll take a look at MIMO, or multiple input, multiple output. And this is actually an antenna technology for wireless communications, whereby you can send multiple signals at once using an array of antennas. Now, these multiple antennas are combined at each end of the circuit, and with respect to each end, it doesn't refer to the fact that there is one on the left and one on the right of something like a wireless router, but rather multiple antennas at the transmitter, multiple antennas at the receiver. So by using these multiple signals, you can minimize errors and optimize your data speed. Now, this is supported by 802.11n and AC. And fundamentally, it's taking into consideration the fact that electromagnetic signals bounce off walls and other obstructions and hence can take different paths from device to device. They are quite literally echoing, if you will. So this causes delays and increased errors with respect to any given transmission. So by using multiple signals over those multiple antennas, you get greater reliability and greater throughput overall. Now, it should also be mentioned that what we are seeing in the graphic here is what's known as single session or single user MIMO. It does not mean that you cannot have multiple users connected. Since the earliest days of wireless networking, you of course could have more than one user connected. But it just means that it kind of has to deal with each session one at a time. So as far as the router is concerned, for example, it sees sessions 1 through 3. And you can imagine this as trying to have different conversations with 3 different people. You can do it, but you have to move from person to person to person. So each person gets their own turn, if you will, with respect to the communication. So clearly it's not as fast. So multi-user MIMO was introduced to, in essence, address that issue. This is an enhanced form of MIMO, and it enables multiple independent radio terminals to access a system. So it uses various algorithms and various methods of multiplexing to effectively allow simultaneous communication with multiple users. And you can see it can actually still use both. It can use the single session capabilities if and or when necessary. So we see sessions 1 and 2 actually being dealt with separately. Then we see 3 and 4 are basically on their own, if you will. So 1, 2 are combined, then 3 and 4 are independent, but all of this is happening at the same time. So with this, now we've got multiple radio terminals. They can provide significant performance enhancement because we now have these multiple users simultaneously accessing the same channel. So with this, we can get significantly higher data rates. For example, in 802.11 AC, the increased theoretical maximum speed is anywhere from 3.47 gigabits per second up to 6.93. Now, you probably won't see those in practical implementations. Those are laboratory tests, if you will, where everything is perfect. But clearly, with this multi-user capability and the ability to have these simultaneous conversations, if you will, the overall throughput can be dramatically increased. In this presentation, we'll take a look at some of the characteristics of the different types of antennas that are used in wireless communications. Now, fundamentally, a radio antenna is used to transmit or receive radio signals by converting electric power into electromagnetic or radio waves. Now, of course, antennas can be huge structures, such as the cell phone transmission towers we often see on the horizon, or tiny enough to fit into a cell phone. So, of course, depending on the device, that will determine the appropriate size and or type of antenna. So the main characteristic really is the direction of transmission. So there are several categories here. The omnidirectional antennas transmit and receive with equal efficiency in all directions. The waves effectively emanate out in a sphere. So examples include radio transmission towers and cell phone antennas. And they have the advantage of being easy to install. They can be mounted virtually anywhere and in any direction. And again, really in any size, depending on how it's being used. In terms of things like networking, or maybe even more specifically stated, home networking, we of course are all familiar with the wireless routers, which have the two antennas on them in most cases. But there is a disadvantage that they typically have a shorter range due to the signal being spread so broadly. For all intents and purposes, there is an awful lot of the signal that is wasted, if you will. There's a huge volume of signal that just is not picked up by any particular device. So the range is not as good, and their efficiency is not all that high. So then, directional antennas have a narrow, more focused directional signal. By design, these types of antennas work more effectively in some directions compared to others. So they are not only a little more effective in any given direction, but more efficient because there isn't that wasted transmission, if you will. So the advantages can offer improved transmission, improved reception of communication, and reduced interference because they are more targeted, more focused. But it can have the disadvantage of effectively being decreased in terms of its width. In other words, if you need that very broad coverage, then directional antennas don't do the job. They are more focused. So again, it depends on the application, really, with respect to is that an advantage or a disadvantage. Now, within the directional, there is also what's referred to as semi-directional, wherein it directs the signal over an arc to reduce unnecessary power usage. Again, just trying to limit the wasted amount of any given signal. Now, I mentioned earlier that the signal emanates out in a sphere, but let's imagine it just more so as a circle in a single plane. If it was omnidirectional across a single plane, the signal would cover 360 degrees. Semi-directional focuses a part of that circle so that it's only maybe 180 degrees, for example, half of the circle, or maybe even less than that. You can focus them in a lot of cases, however, is necessary. And bidirectional antennas would have two high power directions. So again, using the 360 degree example, you could configure a bidirectional to focus one signal for the forward facing 180 degrees and then another one for the backward facing 180 degrees. But you could use them separately. And again, the degree of coverage is actually configurable in most cases. Then there is the Yagi UDA antennas, sometimes just called the Yagi. They have a distinctive arrangement of parallel elements, and this is used as a highly directional antenna, often used for fixed point-to-point systems. And you may have seen this if you've ever watched a nature program where they are tracking a tagged animal. They almost always use this kind of antenna. Very focused, very directional, so it's very good at picking up on a signal once it is able to establish a connection with the specific direction of the transmission. And finally, we have the parabolic dish antennas, whereby the parabola is used to focus incoming signals to a point. So it can pick up on a fairly broad range of signals, but then it focuses them. And of course, this is used in satellite communications and other long-range directional applications. So it's certainly not omnidirectional, nor is it uni, but typically you get a fairly focused portion of that spectrum that is picked up by the parabola and then again sent directly to that single point for processing. So ultimately, the type of antenna is dependent on the device and or the application, but they all have their specific purposes. So
depending on what you need to accomplish with your transmission, that will determine the appropriate type of antenna.
In this presentation, we'll take a look at what's known as site surveys for wireless networks. And there are different types depending on what you're looking for and where you are in your implementation. In other words, you might be assessing an existing wireless network or considering a new implementation. So the first type is known as passive. This assesses the existing access points for signal strength, interference, and access point coverage, and provides a good overall picture of the radio frequency characteristics of an existing wireless network. Now, when performing a passive, there is no actual connection to the access points. You're basically just gathering up very general statistical information about how far the signal carries and what is interfering and things along those lines. So you don't actually establish a connection. And that differs from the active. This gathers very detailed information because you do actually make a connection to the access points. So with this, you get actual network traffic patterns. You can assess the overall throughput and packet loss and determine the actual physical rates. So again, a passive, very general, just in essence, getting the basics. Then the active, you actually establish the connection and gather that much more detailed information. Then the third type is the predictive. This is performed without any type of field measurement. And effectively, this is when you are considering a new implementation rather than assessing an existing one. This uses RF planning software to predict the wireless coverage. So in essence, this is done at an architectural level, often used when the site or the building is not even built yet. So this is helpful for budgeting and planning, of course. So in order to do this, you need some kind of floor plan drawing, either something in AutoCAD or a PDF or a JPEG that can effectively be fed into the software. And then you just use various placements to see what the results might be just in a virtual configuration. So from that point, the next step is documentation. Documenting your findings of any given survey is crucial, and it would take a lot of work to recreate if they were not accurately recorded. So you need to keep track of everything, and you need to be able to produce something, and those findings might also be needed for regulatory reasons. For example, industry or government specific industry regulations that dictate this must be in place and this criteria must be met and that specification must be adhered to. So the main output then of a survey is the site survey report. Again, this is the official documentation, and the report should include things like site maps, recommendations such as the actual network layout, and of course, the potential issues that might arise with respect to the coverage, the capacity, and any interference. The survey map should include any notable locations and materials, particularly a heat map of signal strength. In other words, where is the best signal? Where is the weakest signal? So that, of course, is based on your access point placement, but it simply shows graphically where the signal is at its best and where it's at its worst. So you can obviously avoid placing systems where there is very poor signal. A sitemap should also include existing network coverage and potential future coverage after the recommendations are implemented. Of course, if this is a scenario where you have assessed an existing site. So if it's just being modified, basically you are saying, here's what we have, here's what we should do, and basically, lay out what that would look like. Now, you might also include in this cellular site surveys, but the documentation, while it should be similar, might not be particularly informative. In other words, the recommendations can be rather limited because much of the configuration is simply out of your control. So you can make suggestions such as changing to a different provider, mapping out that this provider looks like that and this provider looks like this. So that one looks better. Let's go that route. And if that's the case, the coverage gaps and the heat maps should be included to justify that recommendation, be able to show that if we change to provider Y from provider X, this is the coverage we will get. So again, you can certainly make those recommendations, but in many cases it is out of your control. But ultimately, it is just trying to get as good a picture as possible of any given site and how wireless transmissions will behave within that site. Okay, in our exercise this time, we'll ask you to describe the 802.11 standards, then to describe cellular technologies, then speed and distance requirements, and finally, channel bonding. So again, what we'd like you to do is to take a few minutes, pause the recording, jot down some responses, and then we'll come back to review and see how you made out. So we'll see you shortly. All right, so for our review, we first asked about the 802.11 standards, and there are several as defined by 802.11a, B, G, N, and AC, and each one varies in frequency, bandwidth, range, and compatibility. Now, G, N, and AC are the newer ones for sure, and do accommodate the fastest speeds and the more stable frequencies, but there are always compromises. Sometimes you want better distance or coverage. Sometimes you want faster speed. Sometimes you need compatibility. So it comes down to which components, which characteristics are of the greatest value to you. So really just become familiar with the characteristics of each before implementing any kind of wireless configuration. Then we asked about cellular technologies, and primarily we talked about the Global System for Mobile Communications, or GSM. And certainly because of the numbers of people that are using mobile communications these days, we need to come up with some form of multiple access. And in GSM, this is accomplished using either TDMA, time division multiple access, or CDMA, code division multiple access. Each one, in essence, uses some kind of scheme to separate my communications from yours so that we don't overlap and we can take advantage of the same media at the same time. Then with respect to speed and distance requirements, this is a function of which implementation of 802.11 is being used. So again, A, B, G, N, and AC all have different specifications when it comes to the speed and distance. So it always depends on which one you are using. And final, channel bonding is the process of quite simply combining two or more channels to increase overall bandwidth. Now, it depends on your configuration with respect to how this is implemented, but at the end of the day, it really is just that combination of channels for increased bandwidth. So hopefully you made out okay with those questions, and if so, we are ready to move on to our next course.